Hello everyone, welcome to my presentation on the validation of a novel floating wind turbine simulation tool. The simulation tool is validated by a benchmarking exercise focusing on a semi-submersible platform. My name is Eigen Analysis. I work for Wood. I'm based in Galway in Ireland. I work in offshore engineering and in the development of numerical simulation software. The purpose of my paper is to validate a novel simulation tool which we've just built recently. The tool combines two separate software packages, namely Flexcom, which is a structural software package used in offshore oil and gas, combined with an aerodynamic solver called FAST, which is an open source software package developed by NWEL. And the two tools combined provide a fully coupled aero-hydro structural simulation capability for offshore wind turbines, both fixed and floating. In terms of the validation process, we're taking the OC4 Semi-Submersible platform, which hosts a 5 megawatt turbine, and we're benchmarking the results obtained using our tool against other existing tools which are already in use in industry. And the presentation highlights some of the synergies between offshore oil and gas and floating offshore wind. In a separate study, we also considered a fixed jacket structure, but for today's presentation, we'll be focusing exclusively on the floating semi-submersible platform. Computational methodology involves the combination of two separate software tools which are complementary. The first is FAST or OpenFAST, which is developed by NWEL. This is an aerodynamic modeling software which is comprised of several component modules, such as Aerodyne, which is an aerodynamic solver, TurbSim, which is a full field turbulent wind input simulator, and Servodyne, which models the control systems on the turbine. On the structural side, we have a tool called Flexcom, which is built by Wood, which is a finite element solver. It also has hydrodynamic modeling capability, so it accepts data from radiation diffraction solvers from potential flow theory, applies these as excitation forces to the floating structure, supplemented by viscous drag forces, which are modeled using Morrison's equation. So the two tools combined provide a fully coupled aero, structural, hydro modeling tool. Just to provide some context, OC4 is which stands for Offshore Code Comparison and Collaboration, is a code-to-code verification project which was sponsored by the International Energy Agency and coordinated by NWEL. The overall goal of OC4 and indeed OC5 and OC6 in that project series is to increase industry confidence in the numerical modeling capabilities of simulation software which exist in the floating offshore wind space. OC4 looked at two different structures. In phase 1 it considered a jacket, fixed bottom platform, and in phase 2 it considered a floating semi-sub. So we're going to focus on the semi-sub today in today's presentation, as this forms the basis for the validation of our new simulation software tool. Here's a model of the OC4 semi-submersible built in Flexcom. It's a relatively small turbine by today's standards. It's just 5 megawatt. Nowadays we'd be looking at maybe 12 megawatt and upwards. But regardless of the turbine size, the numerical modeling procedures are equally valid. So that just shows you an underwater shot there. You can see the various columns of the semi-sub and the cross bracings. Looking at the mooring system there, it's a 3-line simple catenary mooring system, which is quite popular for semi-subs in about this one is in 200 meters of water. Looking in a little bit more detail there on the platform itself, you can see the water level rising slowly up and down on the columns, and just looking up a little bit on top of the tower here, you can just show the tower bending moments as a function of time as the turbine is rotating. Looking first at load case 1.1, which is the Eigen Analysis, or the mode analysis as it's sometimes called. This tells us the natural frequencies and natural periods in the different degrees of freedom for the floating offshore wind turbine. As you can see from the graph there, all of the software tools are in close agreement for natural frequencies in the various degrees of freedom. So for surge, sway and yaw, these degrees of freedom are largely governed by the mooring system stiffness, whereas the heave, roll and pitch the frequencies are largely driven by the hydrostatic stiffness matrix, which is a measure of the changes in buoyancy as the platform moves in the various degrees of freedom. But all of the software tools are in close agreement, which is as you would expect for such a fundamental test case like an Eigen Analysis. Looking on to load case 1.2, which is the static equilibrium analysis of the structure. So it's still water, no wind, no wave loading, and on the graph showing here the tensions in the mooring lines. The first three columns on the graph there refer to the fair lead locations, so the tensions are identical, practically identical from all the software tools, as you would expect, because the tension at the fair lead locations are purely a function of the weight of the suspended mooring line from the fair lead point down to the touchdown point. There's some variations in mooring tensions at the anchor locations, depending on how the friction forces are mobilized along the seabed. So some of the products there don't consider the friction dissipation from the touchdown point to the anchor point, others do. But the discrepancies there are understood and known, and Flexcom is in good agreement with most of the other tools there considered. Load case 1.3 looks at free decay tests in all the 6 degrees of freedom. The graph on the right there just shows platform surge, but equally speaking, there's good agreement between all the software tools for surge, sway, heave, and roll, pitch, and yaw. So there's good agreement in all degrees of freedom. So the free decay tests, the platform is given a certain initial amplitude or initial excitation, and that is allowed to dissipate then over time. And the rate of dissipation is a function of the viscous drag forces which are acting on the structure, namely the skin friction on the body. So there's a fluid resistance as the body moves, and there's also vortex shedding. So all of that is simulated by Morrison's equation, and that's what gives the decay rate here. And the natural period from the decay tests is in agreement with the natural frequency determined from the Eigen solution, which I presented on the previous slide. So moving on to load case 2. All of the test cases in load case 2 consider wave loading without wind loading. So you can see that the load cases build up in complexity as the load cases increase. So load case 2.1 considers regular wave loading only with no wind. There's very good agreement between the various tools for platform heave and platform pitch. On the graph there, we're just looking at the heave response, which is in very good agreement between all tools, as you would expect, because the forcing function in heave is derived from the force REO, which comes from the radiation diffraction simulation, and the resistance to heave largely comes from the hydrostatic stiffness matrix. So all of those should be very consistent across the various modeling tools. So just remaining with load case 2.1 for a moment, still on regular wave with no wind loading, this time looking at platform surge in the graph. And I should have mentioned from the outset that the Flexcom results are always presented in a dashed red line, so you can see that quite clearly on the screen there. So the amplitude of the oscillation of platform surge is consistent across the tools, but the mean position of the surges can be a little bit different. The reason for that is the modeling of mean drift forces in surge is captured by some of the tools better than others. So there's a natural tendency to drift in surge due to second order loading terms from the quadratic transfer coefficients. You also have different frequency effects coming from different frequencies of different wave components, and you also have a phasing effect of the Morrison's drag loads, which get applied at different points in space as the structure moves. So we're expecting a non-zero mean surge position, which is predicted by Flexcom and indeed some of the other tools, but less well by others. But again, the discrepancies are well understood between the different modeling tools, and Flexcom is approaching the correct solution, or the desired solution from our perspective. So remaining with load case 2.1 to fully understand the hydrodynamic response of the structure to wave loading only. This time we're looking at tension in one of the mooring lines, which is the dominant mooring line, which is facing the wave direction, which is picking up the largest tensions. So you can see that the overall magnitudes of the tensions are in very close agreement between the various modeling tools, but there is some differences in the time histories. The reason for this is the approach taken to model the mooring lines. Some tools use a quasi-static mooring approach, which is okay, but it doesn't take into account inertial effects of the lines, or doesn't accurately capture the drag loading properly. Flexcom, on the other hand, and some of the more advanced tools, they show a time history there which has got a dual frequency component to it, because the mooring line is modeled using a full finite element solver, which gives improved accuracy. But overall, there's very close agreement. So moving on to load case 3.1. So load case 3 considers both wave and wind loading combined. So this is similar to load case 2.1 with the exception that we now have steady wind blowing in addition to regular wave excitation. And again, there's quite close agreement. We're looking at platform surge this time, and you may recall from the earlier slide that there was some discrepancy in the mean surge position due to the wave drift effects being captured or not captured accurately enough by some tools. When you apply the wind loading is applied, we get a much closer agreement in mean surge because the thrust due to the wind on the turbine is much larger than the hydrodynamic drift. So this masks any minor discrepancies which existed in the modelling of low frequency second order drift motions in surge, and we get very close agreement between all the modelling tools here. Staying with load case 3.1 for a moment, so it's regular wave excitation with steady wind, which is below the rated wind speed of the turbine. We're now looking at tower base moment, which is a crucial parameter for wind turbine design. It affects the sort of the size and the cost of the tower interface between the tower and the platform. So there's good agreement between the various software modeling tools. One of the tools there probably over predicts the tower base moment, but by and large, the other tools are all showing very close agreement for the tower base moment, which is reassuring. So staying with load case 3.1, which is regular wave excitation with steady wind conditions, we're now looking at generator power as a function of time in the graph on the right hand side of the screen. So in the original OC4 research project, the coordinators didn't focus explicitly on generator power, but given that it's such a fundamental output from a wind turbine simulation, we decided to look at a comparison of our tool called Flexcom against the other modeling tools. And we found a significant variation across the different tools in terms of the generator power predicted as a function of time. So there are a number of possibilities for this discrepancy. It could be different aerodynamic modeling theories underpinning each product. It could be different user options selected during the simulations. Perhaps it could be different platform movements which are leading to slight variations in power. But given that Flexcom is coupled to FAST, we would have expected the Flexcom results, which are shown in dashed red line there, to be much closer to the original results which are produced by NREL for FAST, which is the blue line sort of at the upper part of the screen there. So one peaks at about 2.1 megawatts, whereas the Flexcom results peak at about 1.8 megawatts. So there's a sizable difference there. So we decided to look at that in more detail in a sensitivity study. So staying with load case 3.1, now just looking in detail at a comparison between Flexcom, the new modeling tool which we've been developing at Wood, and the original FAST program which is developed by NREL. So on the right hand side of the screen here, we're looking at the original results produced as part of the OC4 research project, which were presented by NREL, which are shown in blue, and the new results which we've produced using Flexcom. So there's a considerable difference there in the generator power that's predicted by both modeling softwares. So why the difference? Well, it's purely down to the difference in the aerodynamic modeling software which underpins the FAST program. So the original OC4 research project was ran a number of years ago now, and FAST at that time used the Aerodyne version 14 module. Now it's since been updated to Aerodyne 15, and there's been a number of technical enhancements to the Aerodyne solver in the meantime. So it used to use a dynamic inflow theory. It's now using the blade element momentum theory. There have been one or two other minor updates. But when we downloaded the latest version of FAST, which was available at the time of writing of this paper, ran the model with FAST and compared it to Flexcom, we got very close agreement, which you can see by the dashed red line and the orange line on the screens there as well. So we've satisfied ourselves that the differences between Flexcom and FAST, Flexcom and the original OC4 results for FAST, are purely down to a difference in the version of the aerodynamic modeling software. So we're satisfied that the coupling has been implemented correctly and that we're getting out the generator power that we expect from our software, which is really the crux of our validation exercise. So moving on to look at load case 3.2, which is the most complex load case that we've looked at so far in the presentation. This is irregular or random sea loading in conjunction with turbulent wind inflow. So no longer steady wind, but a full turbulent wind input field, and the mean wind speed is at the rated wind speed of the turbine. The graph on the right there shows the mean value of the platform pitch as a function of time across all the software modeling tools, and there's very close agreement. So the mean pitch is about 3 degrees, and there's very close alignment between all the different modeling tools, which is reassuring for this turbulent wind input case. So staying with load case 3.2, we're now looking at the variance of pitch. So for the turbulent wind cases, we don't really look at time histories of the parameters, we look at statistical measures of the parameters. So the variation is the square of the standard deviation of the pitch. So looking at correlation between the different modeling tools there, Flexcom on the right hand side shown in red is in very close agreement with most of the tools. So the variance in pitch is in good agreement. There are 1 or 2 tools which tend or apparently overestimate or are beyond the median or the average of the pitch here, but broadly speaking, our new simulation tool is in very close alignment with most of the other tools which are out there in industry for the platform pitch. Looking now at the mean value of the tower base moment, again for the turbulent wind case of load case 3.2, getting very close alignment of tower base moment across the different modeling tools, which is reassuring, because tower base moment is obviously a critical design driver for the platforms and the tower interfaces. So it's good to see all the software modeling tools giving quite close alignment for the mean value of tower base moment. Looking at the variance in tower base moment, which, as I said, is the square of the standard deviation of the moment over time. This is a random simulation, so it ran for more than 1,000 seconds. So we're looking at statistical measures. Aside from one product there, one software modeling tool, which tends to overestimate the variance in tower base moment, all of the others are shown relatively good agreement for the variance in tower base moment. So Flexcom, our new tool, is showing good agreement with the other tools from the original OC4 benchmarking exercise. So just to summarize briefly the conclusions from the benchmarking exercise and to outline some areas of future work, our simulation software tool has been successfully validated for floating wind applications based on our case study of the deep sea wind semi-submersible platform hosting the OC4 turbine. We've shown very close agreement with the other industry modeling tools in terms of aerodynamic outputs like generator power, rotor speed, and structural outputs like the platform excursions and mooring line tensions and so on. So we're satisfied with the benchmarking exercise. And what I've presented there today is just a flavor of the OC4 results. The actual benchmarking exercise is much broader than I've covered in the presentation. So there's further information in the technical paper, and indeed I have a more detailed report which goes into even more detail than the paper does, and I'm happy to share that with anybody who's interested. In terms of future work, we know there are areas which we can improve upon technically. So some of these would include upgrading the aerodynamic solver from fast to OpenFast. So OpenFast is a new version, a new modularized version of the FAST simulation suite, which is developed by NREL, which is more modern and more modular. So we will upgrade from fast to OpenFast as soon as we get the chance. We're looking at maybe tighter integration with FAST in general. So our TurbSim module, for example, there is a coupling between Flexcom and FAST, but there's a little bit of manual effort on the part of the user. So we're looking to tighten that integration and make the coupling as seamless as possible between the two products. Another area which I haven't really touched on in the presentation there, but we're looking at a more advanced rotor nacelle assembly model. So at the moment in Flexcom, we're using a slightly simplified approach whereby we're assuming that the rotor blades don't deflect in the wind, which is a simplification. So we don't actually model the blades explicitly using finite elements. So we will do that in the next software version, and we'll model the shaft explicitly as well. So there are areas for further enhancements which we are working on and indeed looking forward to in future developments of our modeling tool. Finally, I'd just like to wrap up by thanking a few people by way of acknowledgement. Firstly, Gerard O'Mahony, my co-author, who also works with Wood, So Jared co-wrote the paper, and he also worked extensively on the software development of the coupling between Flexcom and FAST. To Jason Jonkman of NREL, who is the technical lead behind the OpenFast software suite, as I understand it, and Jason also manages the NREL online user forum. So Jason is very, very helpful in helping users with technical queries, and he's answered several of my queries over time. So thank you very much, Jason. And finally, to mention Amy Robertson. So Amy is the chairperson of the OC4 International Benchmarking Project Series, and Amy has been very kind to answer any queries that we have in terms of the OC4 models, and indeed supplying us with data files. So thank you everyone for your time, and I hope you enjoyed the presentation, and I'm happy to take any questions that you may have.